All right, let's jump right in. Today, we're going way, way back to the very beginning of how we even make sense of the world. We're going to explore a single fundamental idea. It's an idea so simple you use it all the time without even thinking, but it's so powerful that it's literally the blueprint for everything from your phone software to the laws of logic.
Just think about that for a second. Before we even had numbers to count with or formulas to solve problems, our most basic instinct was to organize, to look at a bunch of berries or a pile of rocks or the stars in the sky and see them as one thing, as a group. It's a first step in creating order out of chaos.
And that's it. That's the name for this ancient concept. A set. It sounds almost too simple, doesn't it? But trust me, as we're about to see, that one little word holds the key to understanding the entire structure of mathematics. So, let's get specific. We've been talking about this big idea of grouping, but what does a set actually look like when we talk about math? Let's meet the hero of our story.
Here's the official definition. A set is just a collection of distinct objects. That's really it. And the things inside the set, they get a special name. They're called elements. Simple, clean, and you're about to see just how powerful it is.
To make this totally concrete, let's look at an example you for sure already know. The set of all integers, which we call Z. It's just a collection that has 0, all the positive whole numbers, and all the negative whole numbers, stretching out forever in both directions. All those numbers, those are the elements of the set Z.
Now, sets are used for all sorts of things, but they're especially good for grouping numbers. And there are a few really key number sets that pop up everywhere in math and science. Let's get to know the most important ones. Think of it as meeting the rest of the family.
So we've already met the integers, Z. This is kind of our baseline. The whole numbers, both positive and negative, and of course, 0.
Next up, the natural numbers, or N. These are the ones we first learned to count with, right? 0, 1, 2, 3, and on and on. Now notice something. Every single natural number is also an integer. Keep that idea in your back pocket. We're going to come back to it. Then we have the rational numbers, which we call Q. This set is basically any number that you can write down as a fraction. So 1/2, 3/4, even a number like 5, because that's just 5 over 1. This group contains all the integers plus all the fractions that live in between them.
Okay, now we're getting even bigger. The real numbers, or R. This massive collection holds every single rational number, but it also includes all the irrational ones. Those weird and wonderful numbers like pi or the square root of 2 that you can't write as a simple fraction.
And finally, at the top of the food chain, we have the complex numbers, or C. These guys actually extend our number line into 2 dimensions by using something called an imaginary unit. We won't go deep on these today, but it's good to know that this huge set contains all the other number sets we've just talked about. Okay, so we know what sets are. We've met the main players, but their real power, the real magic, comes from how they relate to each other. There are these clear, logical rules that govern how they interact, and this is where it gets really interesting. Probably the most important relationship is the idea of a subset. A set S is a subset of T if, and this is the key part, every single element of S is also inside T. Remember the natural numbers? Since every natural number is also an integer, we can say that the set of natural numbers is a subset of the set of integers. It's like one box fitting perfectly inside a bigger one. Next up is a very special, almost philosophical one, the empty set. And it's exactly what it sounds like, a set with absolutely nothing in it. Now, it might seem kind of pointless, but this idea is absolutely crucial in logic and proofs. Think about it. Because it has no elements that are not in another set, it's technically a subset of every other set. It's a bit of a brain bender, but it works.
This brings us to a really elegant way to prove that 2 sets are absolutely identical. You just do this simple 2-step logical dance. First, you prove that set S is a subset of T. Then you prove that T is a subset of S. I mean, if one box fits inside the other, and the second box also fits inside the first, what's the only possibility? They have to be the exact same size. This 2-way proof is a cornerstone of mathematical logic.
We can also talk about what's not in a set. So imagine a bigger universe of things, let's call it T. And inside it, we have our smaller set, S. The complement of S is just everything else. It's all the elements that are inside the universe T, but are not inside our little set S. It's a way for sets to define both what's included and what's left out.
So we have the definitions, we have the rules, but why does any of this matter?
I mean, why is this simple idea of grouping things so ridiculously important? Well, this is the big reveal.
Because sets aren't just a way to group stuff together.
They are the fundamental language we use to build our entire logical world. At the very bottom, sets are the bedrock of all mathematics. From there, we build the language of logic. And on top of that, we build the architecture for databases and computer systems that run our society. Every single time you search a database, you're actually performing set operations. It goes all the way to the top, where even cutting-edge fields like machine learning rely on these exact principles.
And that, right there, is the ultimate takeaway. Grasping the concept of a set isn't just about learning a little bit of math. It's about understanding that first, most fundamental step we take to bring logical order to a chaotic universe. It's the blueprint for how we think, how we categorize, and how we build the world around us.
It really leaves you with a question to chew on. If an idea as simple as grouping things together is the foundation for so much, what other profoundly simple ideas are out there just hiding in plain sight that might hold the blueprint for everything else? Thanks for digging into this with me.